learning outcomes. At the end of this lesson, students should be able to find the probabilities of the intersection and union of two events. Secondly, find conditional probabilities and independent events. Two events, A and B, are called mutually exclusive if both the events A and B cannot happen together and no elements in common, i.e., A intersect B is an empty set. If event A happens, then event B cannot happen, or otherwise. Only one of the events can occur at one time. The probability of both events occurring is 0. Example, the event obtaining an even number and the event obtaining an odd number are mutually exclusive. This Venn diagram is showing two mutually exclusive events, A and B. There is no intersection between A and B, hence A intersect B is an empty set. Additional rule. So probability of A union B is equal to PA plus PB minus probability of the intersection between A and B. Since the intersection is equal to 0, then PA union B is simply PA plus PB. If n events x1, x2, x3, x4 and so on up until xn are mutually exclusive, then P x1, x2, x3 up until xn is simply px1 plus px2 and so on up until pxn. Example 8. A box containing 3 glazed donuts, 4 jelly donuts and 5 chocolate donuts. If a person selects one donut at random, find the probability that it is either a glazed donut or a chocolate donut. So I'm gonna label glazed donut as G and chocolate donut as C. Using the formula, probability of glaze or chocolate is equal to probability of glaze plus probability of chocolate minus the probability of glaze intersect chocolate. Right. Since we have 3 glazed donuts out of 12 donuts, so the probability is 3 over 12. Then chocolate is 5 over 12 minus 0. There is no donuts that is both glaze and chocolate, so the probability is 0. So add this, you get 2 over 3. Example 9. A bag contains 4 red marbles, 2 white marbles and 8 black marbles. 4, 2 and 8. What is the probability that a marble picked from the bag at random is either red or white? So it's either red or white. Since we already know there is no marble that has both red and white color, then the probability of R union W is simply PR plus PW. We have a total of 14 marbles here. So the number of sample is 14. PR is 4 over 14 plus PW is 2 over 14. Simplify that, you get 3 over 7. Example 10. The events A, B, C, D are mutually exclusive with PA equals to PB equals to 0.3 and PC equals to PD equals to 0.1 if E and F are events defined by E equals to A union D and F equals to B union C. Find these two. Since you already know that A, B, C and D are mutually exclusive and E is the union of AD and F is the union of B and C, that means that E and F are mutually exclusive events. So for E union F, you have PE plus PF. Then using the definition given, PA union D plus PB union C. Then PA union D is PA plus PD, and then PB union C is just PB plus PC. And then you know that A is equal to 0.3, PD is 0.1, and then PB is 0.3. Lastly, PC is 0.1. Add them up, you get 0.8. Then for this one, PE intersect F is equal to 0 since E and F are mutually exclusive events, as I said before. Conditional events. When an event happens is considered with the condition that another event has occurred, then the event is a conditional event. Conditional probability is the probability that an event will occur given that another event has already occurred. For examples, the event that a girl is chosen knowing that the student wears spectacles. 2 balls are taken from a box containing several red and blue balls without replacement. The event that getting the second ball depends on the first ball. Keyword, as you can see here, knowing that, okay, given that, and some other keywords you will find in example or tutorial questions. Formula: the conditional probability of A given B, PA augmented B is equal to PA intersect B over PB, where PB cannot be equal to 0. PA augmented B is read as the probability of A given B. PB augmented A is equal to PB intersect A over PA, where PA cannot be equal to 0. For mutually exclusive events, PA given B is equal to 0 and PB given A is equal to 0. PA intersect B is also equal to 0. So the tree diagram here shows conditional event. To find the probabilities, you must multiply along the branches. So to find the probability of A intersect B here, you have to multiply along these, okay, along these branches. So PA times PB given A, and so on. And you have to add between branches. If let's say you want this probability, okay, and this one right here, for example. So to find the probability of A intersect B complement and A complement intersect B, you have to add these two. Example 11, A and B are two events such that PA is equal to 1/3, PB equals to 1/4, and PA union B is equal to half. Find A intersect B. You already know this formula. PA union B is equal to PA plus PB minus PA intersect B. So you can rearrange this formula to get this formula. Okay, notice the difference. Okay, so now let's use the information given. PA is 1/3, PB is 1/4, and then the union is half. So simplify, you get 1/12. So PA intersect B is 1/12. Next, so for this one, I get the formula from page 8. Okay, you have PA intersect B plus PA intersect B complement is equal to A. So rearrange this, you can get PA intersect B complement is equal to PA minus PA intersect B. Okay, so from that formula, just leave some note here so that you can refer page 8. Okay. So now PA is equal to 1/3 minus intersect A and B is 1/12. So you have 1/4. Next. So this question is quite direct. PB given A is equal to PB intersect A over PA. You already have the intersection between A and B here. A intersect B is just equal to B intersect A. So 1/2 over PA, which is 1/3. Simplify and you get it was 1/12. Okay, so you get 1/4. Let me just repeat that. So the intersection is 1/12, and then over PA, which is 1/3. Okay, then simplify that, you get 1/4. So this one right here, just use the same formula. Okay, I'm using the conditional probability formula, and then since you already know that PA intersect B complement is equal to 1/4, you can just use that information. 1/4 over PB complement. PB is equals to 1/4, so B complement would be 1 minus 1/4. Simplify that, you get 1/3. Example 12. 30 mathematics professors out of 100 who are examined were found to be overweight. Ouch. Okay, 10 of them had high blood pressure. Only 4 of the professors who were not overweight had high blood pressure. Find the probability that a mathematics professor will not have high blood pressure if he is not overweight. So let's draw a table, and let W be overweight, H for high blood pressure, and let's fill the table. So the first one, it says that 30 are overweight. So total of the ones overweight are 30 out of 100. So the sample is 100 professors. Okay, 10 of them had high blood pressure. So total of them that has high blood pressure is 10. So the ones that don't have high blood pressure is 90, and then the ones that don't have that aren't overweight are 70. So 10 of them had high blood pressure. 10 of the ones who are overweight. Okay, so them here referring to the ones who are overweight. So the ones who are overweight with high blood pressure is 10. 20. And then so 4 professors who were not overweight had high blood pressure. Not overweight had high blood pressure, so here. And then okay, the rest you can fill in the table. So this is 66. Yep. So the total for not having high blood pressure is 86, and this one will be 14. Yep. So the question is asking us to find the probability that a mathematics professor will not have high blood pressure if he is not overweight. If, okay, so the keyword here is if he is not overweight. So it is known that he is not overweight. So this is a conditional probability. The question is asking you to find P H complement given that not overweight, equals to, so the formula is P H complement intersect W complement over P W complement. So for H complement intersect W complement, we have 66 out of 100. So 66 over 100 per W complement. So W complement is here. Total is 70. 70 out of 100. So 70 per 100. So you get 33 over 35. Independent events. A and B are independent events if probability of occurrence of event A has no effect on the probability of occurrence of event B, and vice versa. For example, when we toss a coin twice, the result of the second toss will not be affected by the result of the first toss. Dependent events. A and B are dependent events if the probability of occurrence of one event influences the probability of occurrence of the other event. For example, 2 balls are drawn without replacement. The outcome of the second draw depends on the first ball because the condition is changed. Formula: if A and B are independent, then the intersection will be PA times PB. Thus, PA complement intersect B is equal to PA complement times B times PB. And then PA intersect B complement is equal to PA times PB complement, and PA complement intersect B complement is equal to PA complement times PB complement. For conditional events, PA given B is equal to PA if A and B are independent. Okay, if they are independent, then PA given B is equal to PA, and PB given A is equal to PB. Proof: we know that PA given B is PA intercept B divided by PB, and since PA intercept B is equals to PA times PB, then these two will cancel out, okay, and you have PA, same as this. Additional rule, PA union B is equal to PA plus PB minus PA times PB. Example 13, two events A and B are independent. Given PA equals to 1/3 and PA intersect B is equal to 1/6. Find PB. Since we already know that they are independent, so PA intersect B is equal to PA times PB. Then 1/6 is equal to PA 1/3 times PB. We can solve this to find PB, which is equal to 1/2. And then for PA union B, this is equal to PA plus PB minus PA intersect B. So PA is 1/3, PB is 1/2, and then the intersection is 1/6. So you get 2/3. Next one, using the formula, we get this. So the intersection is equals to 1/6, then over PA, which is 1/3. So then we get 1/2. And lastly, so from De Morgan rule, page 8, okay, you can refer that. Okay. We know that B complement intersect A complement is equal to B union A complement. So this is just 1 minus B union A, which is 2/3. So 1 minus 2/3, you get 1/3. Example 14, there are 60 students in a certain college. 27 of them are taking mathematics, 20 are taking biology, and 22 are taking neither math or biology. So for this one, I'll be using table. We have math, then we have biology. So 60 is the number of sample, and then 20 are taking mathematics, so 20 in total 27 in total are taking mathematics, 20 are taking biology, and then 22 are taking neither, so not taking math and then not taking biology. So you have 22. Okay, then just fill in the table. 40, this one is 18, and then 27 minus 18 is 9, and then this one will be 11. Total this will get 33. So for this one, taking both math and biology, you have 9 here out of 60. So 3/20, and then math only, meaning taking math without biology. So you can see from the table, taking math without taking biology, that is 18. So 18 over 60, you get 2 over 3. So a student is selected at random. Determine whether the event taking mathematics is statistically independent of the event taking biology. We already know that M intersect B is equal to 3 over 20. Okay, from here. Then we just need to find PM times PB. So for PM, you have this 27, and then for PB, you have 20. So that gives you 3 over 20. From here we can make a conclusion. Since PM intersect B is not equal to PM times PB, therefore taking math and taking biology are independent events. Okay. Example 15, the probability that Bob is late for college on any day is 0.15 and is independent of whether he was late on the previous day. Find the probability that he is late on Monday and Tuesday. B arrives on time on one of these days. So let's draw 3 diagram first. Okay, choose 3 diagram. So this one right here is for Monday. So we have 2 days here, Monday and Tuesday. So for Tuesday, we still have the probability of being late or not. So late, not late, late, not late. Okay. So this is still 0.15. This is also 0.15. So the probability of not being late is 0.85. Same as here, then here. So the probability of being late on Monday and Tuesday, both days being late. So late and then late again. We have P L intersect L, or you can just write PLL, whatever you like. Then 0.15 times 0.15. Okay, so you times, okay, you multiply along branches. You get 0.0225. Next one, arrives on time on one of these days, meaning either Monday or Tuesday. So either Monday or Tuesday, he will be on time. So late on one day and then on time on the other, or late and then on time and then late. So we have to multiply along the branches and add between branches. Okay, we have to add these 2 probabilities. So P late intersect not late plus P not late intersect late. That will be equal to 0.15 times 0.85. Okay, plus the other one 0.85 times 0.15. You can see from the tree there. The answer would be 0.255.